In the last two videos, I talked about a couple of ways of evaluating the fit of a multiple linear regression model using the regression standard error S and the coefficient of determination R squared. In the next three videos, I'm going to talk about testing the regression parameters in the model, that is B1, B2, and so on all the way up to Bk if we have k predictors. The first test I'm going to consider will think about all of the regression parameters B1, B2 all the way up to Bk. This is known as either the global usefulness test or sometimes the overall test or overall F-test of the model. So here's our model, multiple linear regression model with predictors x1, x2 all the way up to xk. And the question that we're asking is it possible that all k population regression parameters, B1 up to Bk, is it possible they could all be 0? What would that imply if they were all 0? If all of these B1, B2 up to Bk are 0, this part of the model would just go away, and we'd be left with that the expected value of y is just a constant. So none of the predictors would be helpful in helping us predict y. So in most cases, well, I would probably say in all cases, we would hope this is not the case, because otherwise what's the point of what we're doing? So if we pose this as a hypothesis test, we're expecting to reject this possibility. Okay, so let's work through the formal steps of the test. The null hypothesis is that all k population regression parameters are 0. The alternative is at least one of them is not 0. Note that the alternative is not that they're all not 0, it's just that at least one of them is not 0. So all the alternative hypothesis says is that at least one of the predictors is useful in predicting y. It doesn't say all of them are, but at least one of them is. Here's the formula, a couple of formulas for calculating the F statistic. So one method looks at the difference between the total sum of squares and the residual sum of squares, divides that by the number of predictors, k, and then divides all that by the residual sum of squares over the degrees of freedom for error, which is n minus k minus 1. An alternative formula uses r squared instead to calculate the value. They're both equivalent, and typically we're not going to worry about calculating this by hand because we're going to read the number of statistical software. That said, it can be helpful to work through this calculation a few times because it helps with understanding what the test is trying to do. So if we think about it for a sec, what would make the F statistic really large? Well, if the total sum of squares and the residual sum of squares are very different, that would make this a large number. Now, what would make these two numbers very different? Well, the total sum of squares is think of that as just some fixed number representing the variation in the response about its mean. So to make this a very big number, it would be useful if this was a very small number, residual sum of squares. And so what does that mean, having a small residual sum of squares? Well, that means there's very little unexplained variation left in the model. In other words, we've done a good job of explaining the variance in y about its mean, and the predictors are useful. So that's some intuition behind why this F statistic is going to work, because a good model will have a large value for the F statistic. Conversely, what would make this a very small number would be if TSS and RSS were close to each other. And what would make them close to each other? Well, if the predictors really didn't tell us much about the response, then RSS would be fairly close to TSS and we'd have a small F statistic. So that suggests that a large F statistic, we ought to reject the null hypothesis in favor of the alternative, and a small F statistic, we're not going to be able to reject the null hypothesis. Okay, let's set the significance level for the test, and then we can either use the rejection region method by finding the critical value that defines the rejection region, and this is an F statistic, so under the null hypothesis it has an F distribution. And the F distribution is a probability distribution that's indexed by two different degrees of freedom, a numerator degrees of freedom and a denominator degrees of freedom. And unsurprisingly, the numerator degrees of freedom is given by this number here in the numerator of the F statistic formula, so K, the number of predictors, and the denominator degrees of freedom is given by this number here in the denominator of the calculation. So n minus k minus 1 denominator degrees of freedom. An F test is always upper tailed. So it's a 5% test, so we put 5% in the upper tail and we look for the 95th percentile to define the rejection region. Alternatively, we could use the p-value to make our test decision. So that's going to be the area to the right of the F statistic for this F distribution. And then if our F statistic falls in the rejection region, or equivalently, if the p-value is less than the significance level, then we reject the null hypothesis in favor of the alternative hypothesis. Otherwise, we fail to reject the null hypothesis. So here's a picture of a density curve for an F distribution, and in this picture I've got the test statistic here falling in the rejection region because the critical value is here, and so the test statistic is falling in the rejection region. And I've also got the p-value, which is the tail area beyond the test statistic, being smaller than the significance level, which is the tail area beyond the critical value. So this is typically what happens in a multiple linear regression analysis, is we end up with a global F statistic or a overall F statistic that's in the rejection region with a p-value smaller than our significance level. So let's work through an example. So we're going to look at the Holmes 3 data. So this is the one that we've been looking at throughout this chapter. It's with sale prices modeled using two predictors, floor size and lot size. And this was our model, and this was our output. And you can see here down at the bottom, F statistic 51.43 on 2 and 3 degrees of freedom. And a p-value of 0.00477. So that corresponds to these results up here, just slightly different rounding. But there's the F statistic, the overall F statistic or global F statistic, and there's the p-value right there, 0.005. So if we use the p-value method, our p-value is smaller than our significance level 0.05. We reject the null hypothesis in favor of the alternative, and we conclude that, let's go back to our null and our alternative. We're rejecting this in favor of this, so at least one of the regression parameters is not equal to 0. So that means at least one of floor size and lot size is useful in predicting price. The remainder of this slide just runs through calculations that can help you practice understanding what this formula is doing. So here's total sum of squares, it's this number here. Here's the residual sum of squares, it's this number here. Okay, and there's k, two predictors. N is 6, sample size of 6, minus 2, minus 1. So we're going to have 2 in the numerator, 3 in the denominator. That's what this means here in the output. 2 degrees of freedom in the numerator, 3 degrees of freedom in the denominator. And there's RSS again. We can also use the R squared formula, the formula that has R squared in it. So there's R squared, and there's 1 minus R squared. Either way, you end up with 51.4. You end up with this number here. The critical value is the 95th percentile of an F distribution with 2 numerator degrees of freedom and 3 denominator degrees of freedom. I can calculate that in R using this function here. This code here is the code that you could use in Excel if you were using Excel to find your critical values and p-values. The p-value is, I can obtain that using this function here, except I've not calculated these things yet, so let's just do that. There we go. So there's the p-value there using the pf function. And again, this is from Excel. So either way we get 0.005. Or easier still is just read the number off the output, this number here, 0.00477. So we reject the null in favor of the alternative. At least one of the predictors is linearly related to y. Okay, let's finish up with working through the global usefulness test, or the overall F-test for the shipping department data. So let's go back to that. So there's our model with all 4 predictors. And here's the output that we need down at the bottom. I get an F statistic of 17.03, so this question mark would be 17.03. This one is the p-value, that would be 1.9 times 10 to the minus 5, so pretty small number, close to 0. So this global F statistic, that's the 17.03. Our critical value, if we do it in R, we get 3.06, and then if we're going to calculate the p-value by hand, we can use this code using the pf function, and there's our p-value there, 1.9 times 10 to the minus 5. So our conclusion, again, rejecting the null in favor of the alternative because our test statistic is in the rejection region, or equivalently, our p-value is less than 0.05. So we conclude at least one of the predictors is linearly related to y. So that's the global usefulness test, or the overall F-test. In the next video, we'll move on to thinking about whether a subset of the predictors is needed in the model. So we're going to test a subset of the regression parameters, whether that subset, all the regression parameters in the subset are 0.